So the first talk of today will be given by Professor Anna Mavrogianni. Anna is an assistant professor in sustainable building and urban design. She is an expert in indoor environmental quality, building energy retrofits, and climate change adaptation of the built environment, focusing on heat vulnerability and air quality at the building and urban scale. She has produced more than 120 peer-reviewed publications and contributed to policy reports, including the UK government's climate change risk assessment. She is a co-secretary of International Building Performance Simulation Association in England and an associate editor of Energy and Buildings. The title of Anna's talk today is Climate Resilience and Indoor Environmental Quality in Buildings Occupied by Vulnerable Populations. So now, Anna, the floor is yours.
Thank you very much, Professor Wong, and also many thanks to Professor Lin, as well as Dayan for inviting me to speak today. I'm really honored to present during the first event of this really exciting joint collaborative series between Tsinghua University and UCL IED. The focus of my talk today is on outputs from a series of research projects I've been involved in the last few years. And a common thread of these projects is that the focus on buildings occupied by vulnerable populations. So I'll start with giving some context, explain a little bit the rationale behind this research work, and then I'm going to present those projects on schools, housing, and care homes. And I'll end with some thoughts for further research. And I'd just like to mention that these projects are the result of collaborative work, and I'm really happy to see that some of my collaborators are attending today. So as we all know, climate change will increase the frequency and magnitude of extreme weather episodes across the globe. What does this mean for the UK or other climate regions with similar weather conditions, so heating dominate climates or even temperate climates? The UK in particular will become warmer and wetter and windier in the winter, but we'll start experiencing much hotter and drier summers. And we have already experienced this type of warmer weather in the summer. For example, the catastrophic European 2003 and 2006 heat waves, but also more recently we had quite warm summers in 2018 and 2020. At the same time, we experience significant urbanization trends, and we expect that by the middle of the century, around 70% of the population globally will be living in urban environments. The risk of overheating in urban environments is magnified by the urban heat island effect, which is this phenomenon of inadvertent climate modification, which is linked to urbanization. But what I'm particularly interested in is what we call multidimensional vulnerability and how this is likely to interact with climate change related risks. So this is a graph taken from an IPCC report, and we can see how multidimensional vulnerability can be defined. And we talk about markers or dimensions of inequality in relation to gender, class, ethnicity, age, race, disability, etc. And these are, they interact with each other, and they result in systemic inequalities that then might interact with current and future climate change related risks. And we talk about vulnerable population in the sense that people's capacities and opportunities to adapt, cope, and recover from climate change events is diminished, is reduced. An interesting example of this is the overlap between heat risk factors and COVID-19 risk factors, and there have been some publications on this recently. Going back to the UK, and I guess that's quite similar in other countries as well, we have a rapidly aging population, and this is likely to lead to an increased need for care provision in the future. And we also know that older populations are more vulnerable to heat stress. So epidemiological studies demonstrate that it's usually people above 65 years of age that are more vulnerable to heat-related mortality and morbidity, and also people who suffer from chronic conditions such as cardiovascular or respiratory disease. So what are the challenges for the built environment? What does it mean for us as researchers or practitioners in the built environment? So we know that the indoor environment is a key moderator of heat as well as air pollutant exposure in vulnerable populations, especially as they tend to spend the majority of their time indoors. And in many ways, the COVID pandemic has really highlighted the importance of indoor environmental exposures for human health and well-being. And some initial evidence indicates that newly constructed schools, homes as well as care homes today in the UK are already overheating, even under non-extreme summers, or might be experiencing poor indoor air quality. And we expect, of course, such overheating risks to be exacerbated as a result of climate change. And what we find is that there is an evidence and knowledge gap, as well as a lack of simple, easy to follow guidance on how to design or retrofit those buildings that are occupied by vulnerable people in the context of climate change. So many researchers and construction industry practitioners have been talking about this for quite a while, and these are some examples of policy or industry-led reports that have been published in the last few years highlighting this problem. And there is a wide range of actors affected by this problem: the construction industry, landlords, in particular in the social housing sector, the healthcare sector, and the people owning and, of course, inhabiting those buildings. But a lot of researchers have also been talking about a perfect storm of interacting factors, or a toxic cocktail, if you'd like, of interacting factors. So we talked, of course, about climate change and urbanization, but at the same time, we have in the UK and elsewhere climate change mitigation targets, so quite stringent energy efficiency targets for new buildings or retrofitted buildings. So there is this huge drive to increase the thermal energy efficiency of our existing and new building stock by increasing thermal insulation or building fabric airtightness. And this can sometimes, if not implemented correctly, can lead to increased exposure to excess temperatures or trapping of indoor air pollutants. At the same time, there is a drive to reduce construction costs, and this means that some measures, for example, shading might be the first one to go as we're trying to reduce cost. Increasing land and housing prices. There is a significant lack of technical skills, so it's upskilling has been promoted as a significant priority, growing skills in the industry. And until recently, building regulations did not fully cover things such as overheating mitigation. This has changed in the UK. So we have a new part for the mitigation of overheating, which is coming into force next month. But in my opinion, in addition to these factors, there is also an element of socio-cultural lack of knowledge about how to deal with heat or poor indoor air quality, and also the invisibility of the problem. So we can't see temperature. Thermal comfort is a subjective variable, if you'd like, with many parameters, and overheating problems are not as visible. They can't be visualized as flood risk, for example. And similarly, we can't see indoor air pollutants. Some harmful air pollutants can be odorless, for example. And of course, public awareness about outdoor pollution has been increasing in recent years. And hopefully we'll see something similar about indoor air pollution. And I guess this is a silver lining of the COVID pandemic that increased awareness about the importance of the indoor environment. So I'm now going to talk about these outputs from these three projects. So as you can see, these are large-scale collaborative projects. And as I said, some of the people leading or collaborating in these projects are online today. So I'll first start with the Aspire project, and I lead together with Professor Dejan Mumovic. This is a project funded by the Engineering and Physical Sciences Research Council in the UK. It was a 2-year project, and it's going to end this summer. So the project aimed to address a key knowledge gap. Can school buildings achieve low carbon emissions while simultaneously maintaining high indoor environmental quality that enhances both learning and health? And our objective was to create a toolkit for a wide range of stakeholders that could help them assess the relative impact of design and operation strategies. So this is a diagram illustrating the various interlinkages between the different work packages. So we start with a review of existing data and information about existing health and performance effect relationships. And also we analyze a large-scale data set of school properties in the UK. So the statistical analysis of this fed into the development of a school building stock model, and that's archetype based. And by using the stock model, we run it for a range of scenarios, and this will feed into a health impact and cost effectiveness analysis study led by our colleagues at the London School of Hygiene and Tropical Medicine, as well as a multi-criteria decision analysis framework. So these are some results from the analysis of this database. So you can see the distribution of school buildings by region, and here by construction age band. So some of the stock is indeed quite old. By natural and mechanical ventilation, so the stock is primarily naturally ventilated, as well as by type and presence of extensions. So these are the 5 construction age bands for which we have developed a series of archetypes. So as you can imagine, the building characteristics vary by construction age band. And this kind of summarizes the structure of the model. So we start with simplified seed model geometries, then we assign building fabric characteristics through the PDSP database. And the core calculation engine is the Energy Plus software with some post-processing happening in Python. And the outputs are a range of indoor air pollutants, energy use, temperature, and humidity. So this is a paper that came out recently, published in the Buildings and Cities Journal, and I have to thank our researcher Duncan Grassi, who led this study. So this was part of a special issue on alternatives to air conditioning, and as you can see there, we model a range of scenarios, different energy retrofit as well as passive cooling strategies. So I won't go into a lot of detail, but the paper is open access, so it's freely available for you to read. But I'll just briefly mention some key outputs. So we found that the most recently built archetypes, so post-1976 school buildings, were the ones most prone to overheating. And this is indicative of this conflict between having better insulation, higher air tightness, and overheating prevention. We found that a range of retrofit and passive cooling measures could mitigate against overheating. However, there is kind of a limit to the technical feasibility of those measures and their ability to limit overheating. And we found that probably some type of mechanical ventilation might be required towards the 2080s in order to maintain indoor temperatures at acceptable levels. And while there was no one-size-fits-all approach, so no single measure had universally positive effects, overall night ventilation and overhangs were found to be particularly effective measures against overheating. So the next steps will be to quantify the impacts of low carbon school design on the health of school children. So there's this cost effectiveness analysis work led currently by our colleagues at the London School of Hygiene and Tropical Medicine. And this will fit into this multi-criteria decision analysis framework tool that is currently under development. And we hope that this is going to be a useful tool for policymakers to compare policy and interventions options across a range of criteria, including indoor air quality, health, education attainment, cost, etc. So I'd like now to move on to another project, the Health Protection Research Unit in Environmental Change and Health. So this is a large-scale research project funded by NIHR. It's led by the London School of Hygiene and Tropical Medicine, but this specific component of the work is led by Professor Mike Davis. So this research investigates the impact of housing, climate change mitigation adaptation measures, and has a specific focus on critical changes in ventilation parameters and the balance of effects on health as a result of changes to indoor air quality as well as other adaptations. So this has built on previous work carried out for a previous HPRU project. And in the context of this project, the team developed a meta-modeling framework based on neural networks that can rapidly estimate indoor temperature as well as air pollutant exposures under a range of scenarios. So this is also an archetype-based model for housing in the UK. It also uses Energy Plus as a score calculation engine, but has this ability to quite rapidly estimate changes to indoor environmental quality exposures across the stock. So these are some results from an older paper led by my colleagues Jonathan Taylor and Phil Simmons, who I think is on the line, for which we evaluated the impact of energy efficiency retrofits as well as overheating mitigation strategies in housing in the West Midlands. So what we found was that full energy efficiency retrofit can significantly reduce space heating demand, but also led to some increases in summertime overheating as well as associated risk of heat-related morbidity and mortality. But external shutters were found to have a quite protective effect. So I guess the takeaway message from that study was that having adequate post-retrofit ventilation, the installation of shutters, especially external shutters, and ensuring the windows can be operated so that we have this cooling benefit from ventilation, particularly in homes occupied by heat-vulnerable people, could at the same time save energy, so achieving our climate change mitigation targets, but also significantly reduce heat-related morbidity and mortality. So this is another paper that came out of this work where we mapped overheating risk as well as air pollutant exposure across the UK housing stock, so the national level. And some of the results corroborated findings from previous studies on overheating. So it was top floor flats or the more newly built airtight terrace dwellings, as well as bungalows with high levels of glazing that were found to overheat the most. We also found that wind exposure was quite significant for indoor air pollutant exposure across the country. And in this paper, the model was adapted to include indoor air pollution from outdoor as well as indoor sources. And interestingly, it was found that nitrous dioxide concentrations were higher in London dwellings. So this could be quite significant, especially when we look at lower income neighborhoods that might have some restrictions with regards to ventilation due to security or outdoor pollution concerns. And this is the last project I would like to talk about. It's a project focused on the climate resilience of care homes, again led by Professor Mike Davis. So the aim, we started with a pilot project, and now we move to a larger scale project. And our aim was to cover this knowledge gap that exists about the climate change adaptation potential and current overheating risks in care homes in the UK. Because I think a lot of work exists on homes, schools, office buildings, but less is known about the building performance of care homes. And I think one of the challenges is that they tend to be hybrid spaces, so that they're in residential settings for the residents living there, but also the function as workplaces for frontline care staff and other people working there. So they present quite significant, quite unique challenges, if you'd like. So our aim, this is primarily applies for the pilot project. Our aim was to carry out monitoring work in a number of UK care homes. So I think at the moment we have our colleagues at Oxford Brookes University who lead the monitoring part of the study have, I think, recruited between 30 and 40 care homes. But today I'm only going to present some findings from the pilot study and assess the impact of heat exposure on the health of residents, but also employ building performance simulation to test the range of the impact of a range of retrofit scenarios to current and future overheating risks, but also work with different stakeholders, care home practitioners, policymakers, and combine multidisciplinary research perspectives in order to provide guidance that's tailor-made for stakeholders moving forward towards their adaptation to climate change. So these are the 5 care homes we studied during the pilot, and they were monitored during the summer of 2019. So even though the sample was quite small, you can see that we achieved quite a good coverage of. We included different construction age bands, a good mix of purpose-built as well as converted care homes, and quite a good range of different sizes, from very small to fairly large care settings. So monitoring was carried out using HPRU data loggers, so measure temperature, relative humidity, and carbon dioxide levels. And this was combined with a number of surveys that investigate the thermal comfort perceptions of residents, and also semi-structured interviews with the care home managers and staff to understand heat management practices and potential barriers to the implementation of heat risk mitigation strategies. This is some modeling work led by my colleague Eleni Konomou. So we use dynamic building performance modeling, again, Energy Plus, and with the Design Builder graphic user interface. We test a number of weather files for the current and future climate change. And we test a number of building fabric retrofit scenarios, as well as behavioral change adaptation. So we split these measures into what we call non-structural or soft measures and structure/hard engineering solutions. So the first ones are what we call the low-hanging fruits, primarily related to different operational strategies, whereas the second ones are perhaps more disrupting, high cost, more technologically focused solutions. And this again summarizes the type of interventions that we can test through our modeling framework. So we found that in the summer of 2019, in those 5 case study care homes, occupants in older heavyweight buildings were less likely to feel hot in the summer. It was again the more recently built care homes that tend to overheat the most. But we also found that daily maximum temperatures were often much higher than the recommended 26 degrees Celsius threshold. And that's even though, as you can see, the summer of 2019 it was relatively mild. It wasn't that hot. The modeling work indicate that older buildings appear to benefit more from the application of high reflectivity materials, whereas the newer buildings appear to benefit more from achieving higher ventilation rates and installing external shading systems. But across the board, the most impactful measures lie in the area of passive ventilation and heat management. And the most effective measure was the use of night ventilation. But of course, there is a question there about feasibility, especially when we're talking about ground floors. So in summary, that combination of soft and hard engineering passive strategies was capable to reduce indoor temperatures quite significantly. Again, there was no one-size-fits-all approach, with different measures being more effective for different construction age bands, different archetypes. but night ventilation and overall increase in ventilation rates being a quite effective measure, at least for the current climate. Again, this is likely to change in the future as external ambient temperatures increase and have less of a cooling benefit. So this is the website we have, and these are some reports we produced primarily from the pilot that are again publicly available online that you can access. And I think they provide quite nice summaries of the project. But of course, work is ongoing, and we're currently doing some cost-benefit analysis work. And in terms of next steps, so as I said, we have recruited a much larger sample of care homes to monitor, and we are building this strategic multi-stakeholder platform involving a wide range of actors, including building construction practitioners, policymakers, in particular public health policymakers, but of course care home managers, frontline care staff and the residents themselves. And the aim is to empower them in order to produce best practice guidance for the climate change adaptation of care settings. And I'd like to finish. I don't know how we're doing for time. Sorry, apologies. I can't see the time as I'm sharing the screen. But I'd just like to finish with some thoughts for further research. So as you saw, our projects tend to be interdisciplinary, integrated building design and multi-stakeholder co-creation is absolutely crucial. I think the type of research challenges we are facing cannot be addressed without the involvement of several stakeholders. I also think that a lot of the problems we're facing tend to be of socio-technical nature. So we need data on human behavior and a better understanding, if you'd like, of the human building interaction components. And I'm again very interested in the intersection between the impact of our building design and retrofit decisions on human health and well-being and socioeconomic inequalities. And I would also like to mention, in relation to inequalities, a special issue I co-edited back in 2020 with Dr. Sonia Klinsky from Arizona State University in the Buildings and Cities Journal. So we collect a number of really interesting papers. This is also open access, and you can follow the link and read those very interesting papers on the role of the climate justice and the role of the built environment. And I think that's my last slide on integrated building design. Back in October 2020, we launched this free webinar series on integrated building design led by UCL IED. So most of the talks, it was run approximately on a monthly basis. And most of the talks we had to date are available to watch online on our YouTube channel. So if you follow this link, you can access the talks by various industry speakers, some really excellent examples of integrated building design. So thank you very, very much for your time. Again, please feel free to drop me a line after this event if you'd like to discuss any of the outputs that I presented. But I'd also be very happy to take questions now. And thanks again to Tsinghua and IED for inviting me to present today. Thank you.
Thank you, Anna, for your very brilliant talk. So I would like to invite any participants to type in your question if you have, or you can also unmute yourself to ask. So, I mean, maybe actually, Anna, I have a question for you. Maybe I can start with myself. Sure. So we all know that the COVID pandemic significantly impact our lives and of course our building industry. For instance, ASHRAE has basically required like all the commercial or large residential buildings to maximize their ventilation requirements, basically to give up the strategy of reducing ventilation based on the number of people indoors. So I guess like all of your studies present today was conducted before the pandemic. So my question for you is, at least to me, like the COVID is like endless. So my question for you is, how do you think the COVID or the pandemic will shift us from our focus from addressing the climate change to addressing like the pandemic? And I mean, in terms of energy consumption, in terms of the indoor environmental quality for buildings. Thank you.
Thank you so much for this question. I think you raised a really important point. So you are right. So the projects are presented in their majority, they were devised, if you like, pre-pandemic, but of course they're ongoing, and they're influenced one way or another by the new requirements, especially for ventilation following the COVID-19. So yeah, ASHRAE has those recommendations in the UK. Similar guidance has been published by CIPSI, the Chartered Institution for Building Services Engineers. And I think what we see is this shift from the need, to achieve ventilation rates in relation to, keeping indoor pollutants at sufficiently low levels, so improving indoor air quality, especially in winter, to achieving much higher ventilation rates for disease transmission control. So there's a shift between indoor air quality, or cooling in the summer, to disease transmission control, and the rates that we need to achieve for the latter are of course much higher. So I think there is still quite a lot to do in terms of trying to find a balance between heat loss through increased ventilation in winter and achieving appropriate ventilation rates for COVID, or if we ever face another pandemic. But I do see it as a positive step, and I think there have been some voices, if you'd like, that have highlighted that there might be synergies between actions to improve our buildings during and post-pandemic, and adapt to and mitigate climate change. So I think it's all about identifying co-benefits. For me, the important thing is what I mentioned during my presentation, that increased awareness about the importance of the indoor environment. I see that as the silver lining, if you'd like, of the pandemic. But I think, yeah, there's still quite a lot of work to be done there. But it's interesting that some of the what I said about some heat risk, heat vulnerability factors tend to coincide with COVID-19. And during the summer of 2020, for example, we had a lot of people, self-isolating in residential environments that might have been overheating. Yeah, I think there is a lot of more research to be done in this area. Thank you.
Thank you. And I think we have a couple of questions on the chat. So
shall I respond to the first one?
Please, yeah.
So there's a question about the politics of implementation of this kind of projects. Thanks for the question. Could you please explain a bit more, if you'd like? What do you mean with politics? I don't know if Leonardo could hear us.
Maybe we can start from the next one, which is about basically Deng Ruiwen is asking, could you please introduce more about the novel measurement techniques for evaluating the heat exposure impacts on residents' health in ClimaCare project? Thanks.
Yeah, thanks for this question. So originally we intended to do some experimental work on measuring body temperature of older residents in care homes, but there have been some issues with research ethics, so I won't go into more detail on this. But in the larger scale project, we hope that we might be able to work more on this. The next question, have you reviewed the effects of biophilic design with the design outputs of buildings, especially the mental health benefits? Yeah, that's an excellent question. We haven't, but as I'm involved as Deputy Director in the MSc Health, Wellbeing and Sustainable Buildings program, and quite a lot of our students every year carry out their dissertations on biophilia. We have a number of outputs, not with so much focus on mental health, at least not this year. But yeah, we've had some very interesting studies on impacts of biophilia on work productivity, and as well as thermal comfort perceptions. But yeah, it's something that we should be researching more in the future, absolutely. So there is a question by Gavin, whether the airtightness requirement in the UK building regulation contributes significantly to overheating in the summer. And yeah, so quite a lot of our work has showed that indeed increasing the airtightness of building fabrics can increase overheating in the summer. And this is because you tend to lose those air exchange pathways. So in older buildings rely on that leakiness to have that cooling benefit. However, I think this is, again, it's a design problem. So as long as you achieve appropriate design ventilation systems appropriately, this shouldn't be an issue. And what do you think the cooling measures will be adopted in the UK, such as ceiling or air conditioner in dwellings? So as you know, air conditioning penetration is quite low in the UK. I think the most recent data I've seen suggests only 3 or 4% of homes in the UK have an active air conditioning system installed. However, this is likely to increase in the future, especially as we have a building stock that's not adapted to warmer weather, and lack of funding for retrofit. So there is no prioritization of, say, passive low carbon cooling solutions. Then of course the easy fix will be for people to go out, purchase an air conditioning and operate it. But of course this starts this vicious circle of increasing carbon emissions. I mean, there might be other solutions such as heat pumps used for cooling, but again, we should be seeing this holistically in terms of the overall carbon footprint of a building. But I'm quite hopeful that the new the revised building regulations, should be able to contribute to the increased implementation of passive cooling measures across the UK, the English and Welsh housing stock.